Welcome to the next video on kinetic energy and potential energy. So what we learned in the last video, we know that work is defined as W equals force times distance or displacement. And we can use this relationship to help us find the translation of work in moving energy. I'm going to show you how I'm going to derive our kinetic energy formula. So the first thing we know is that force is equal to ma. I can rewrite this by changing A to a kinematics equation of Vf minus Vi over t, so the change in velocity over time. We're going to assume that our initial velocity is 0, and if we do that, then we're going to get force is equal to m multiplied by V final over t. So this is one result I'm going to use later on. The other thing I'm going to look at is the equation for the change in displacement. We know from our kinematics equation that this could be Vf plus Vi over 2 times t, one of our 4 kinematics equations. Again, I'm going to assume that Vi is 0, and then I'll be left with Vf over 2 multiplied by t. Again, this is if Vi is equal to 0. So I'm going to use this equation and this equation to derive our kinetic energy formula. Here is the last part. We know that work is force multiplied by distance or change in displacement. I'm going to change F with the first equation we found with m multiplied by Vf divided by t. I'm going to change our distance as Vf over 2 times t from our second equation that we found. And then I am going to simplify this. So we get a half, our time cancels out, so that's gone, and we're left with mvf squared. Therefore, our equation for kinetic energy is a half mass V final squared, or V squared. And this is called kinetic energy. When work is being done on a moving object, it will result in a change in kinetic energy. Therefore, W, work, is the change in Ke for kinetic energy. Let's do an example of this. What is the kinetic energy of a 1,500 kilogram car moving at a speed of 85 kilometers per hour? For our kinetic energy formula, all we need is the mass and the velocity. We have the mass already. Our velocity we have as well, but it's in the wrong units. It's in kilometers per hour. So we do need to convert it to meters per second. So if I want to convert this into meter per second, I'm going to multiply it by 1,000 divided by 3,600, which is 23.6 meters per second. Okay, the next step is putting this into our formula for kinetic energy. So our mass is 1,500. Our velocity is 23.6 meters per second. So our kinetic energy is 4.2 times 10 to the power of 5 joules. Here's the second part to that question. The car above hits a snowbank and comes to a stop in 6 meters. What is the chance in kinetic energy? What is the change in kinetic energy? And what force was exerted on the car? So our change in kinetic energy is going to be the final kinetic energy minus the initial kinetic energy. Our final kinetic energy should be 0 because it comes to a complete stop, so there is no energy there. But our initial energy, we just found that in the previous example, and it's 4.2 times 10 to the power of 5 joules. So our final answer is negative 4.2 times 10 to the power of 5 joules. And that is our change in kinetic energy. Now, that was one part of the question. The second part of the question asks about the force. We know that work is force times distance, or that is a change in kinetic energy. So I'm going to use this part to help us find force by rearranging that. By dividing by d on both sides, we're actually going to calculate the change in kinetic energy over our distance. Our change in kinetic energy we just found is 4.2 times 10 to the power of 5. Now it was negative, and then we're going to divide it by the distance traveled, which is 6 meters. So our final answer for the force exerted on this car is negative 7 times 10 to the power of negative 4 newtons. Moving on to potential energy. So we're going to use potential energy when we raise a mass above the Earth. And when this happens, we do work. Energy is stored because once you release the mass, it will fall back to the surface of the Earth. That stored energy is equal to the work done to lift that mass. So we're going to consider a mass m moved a distance h. If we want to find the force to lift the mass, it's going to be the weight of that object, which is calculated as Fg equals to mg. And we also know that work is force times distance. That force can be replaced with mg. And our distance, we're going to say that's h. And this is our formula for potential energy. Just as a side note here, at h, all work becomes potential energy. So when we're talking about, let's say, a cliff here, and you're releasing a ball from this cliff, at that point, this is all potential energy here, because it wants to fall down. So what is the potential energy of this object once it falls back to the surface of the Earth? When your height is 0, that means when our ball or whatever object it is on the ground, your potential energy is going to be 0, and now it's all kinetic energy. Okay, so once you're at, let's say at a top, and you're trying to make something fall down, you have full potential energy because the object wants to fall towards the Earth, but once it's at the Earth, when it's touching the ground, it becomes kinetic energy. Let's do an example of this. A mass of 15 kilograms is thrown 15 meters into the air. How much work was done, and what is the potential energy of the object at 15 meters? So we want to find the potential energy, which is calculated as mg multiplied by the distance h. Our mass is 15 kilograms. Gravity is 9.81 meters per second squared. And then your height is 15 meters in the air. So the work being done is 2,200 joules. So as the object falls, the potential energy that it has will be converted into kinetic energy. The total energy of the object can be expressed as the sum of potential and kinetic energy, defined as the following. Energy total is equal to potential energy plus kinetic energy. So as the object falls, your potential energy will convert to kinetic energy. Let's do an example of this. A ball of 2 kilograms is released from a height of 10 meters. What is the speed at 5 meters from the ground? So we're going to first find our potential energy. And this is calculated as mg times h. Our mass is 2. Gravity is 9.81 meters per second squared. And your height above the ground is 10 meters. Remember, your full potential energy is the very top of that height, which is 10 meters. So your potential energy there is 196 joules. So just as a side note here, at 10 meters, remember that your kinetic energy is going to be 0 because that is where our ball is being released from. So our total energy, if we were to combine a potential and kinetic energy, your total energy is just made up of your potential energy at this point, which is 196 joules. Okay, so now let's look at the scenario when we're at 5 meters, because we're trying to find the speed at this time. We know that the entire energy is the sum of potential and kinetic energy. And we also know the entire energy is going to be 196 joules. And that's what we got from part 1. I'm going to replace potential energy with its formula of mass times acceleration due to gravity multiplied by our height plus the formula for kinetic energy, which is a half mass times velocity squared. I'm going to fill in the information we do know. So mass is 2 kilograms, gravity is 9.81 meters per second squared. The height we're looking at is 5 meters in this case. The mass of the object is 2 kilograms, and we're looking for V. So I'm going to do some rearranging here so we can solve for V. So 2 times 9.81 times 5 is 98 plus V squared, because 2 divided by 2 is 1. Subtracting 98 on both sides, we're going to get 98. And then we want to square root both sides, so V is 9.9 meters per second, and that is our final answer.